Thanks, Carol, and Dr. Tao for inviting me to talk today. I feel like I'm on double duty, talking yesterday as well, and actually I'm using the first slide over again, except I changed the title, Long-Term Acidification, Obvious and Hidden Dangers. And I really like this shot of a soil profile taken at the Cook Agronomy Farm, so just outside of town here. And it shows two distinct horizons that are enriched in carbon. And so, but there are different kinds of carbon. So up here we have organic carbon. It's associated with this dark color. And here you can see the carbonates that are in this particular soil. And not all our soils have carbonates that are in this rainfall zone that we have here, but there's certain landscape positions that do. So this is a staley soil. It's tends to be on some eroded knobs that we have. So there's a history of erosion that's taken place on this particular soil. You can see the slope. It slopes down from here. And you can see the distinct plow layer here in terms of past activity in terms of tillage. And if you know something about this soil, you'll realize that, oh my gosh, there's a whole horizon that used to be here, but it's no longer here. In other words, above these carbonates, there used to be a B horizon that didn't have carbonates, or as many carbonates. And then through the action of erosion, of course, that takes soil away from the top, and then the plowing, which basically incorporates the subsoil, we've been basically liming these soils with tillage, over time in terms of basically biting into carbonates that are in the subsoil. This is not what I would call a preferred practice in terms of liming soil, in terms of using tillage to do so, but it's definitely has happened. But it's also created then differences in soil pH across our fields. Those locations that had some of these carbonates in the subsoil definitely tend to be higher in pH in the surface, in this plow layer as well, than other locations in the same field that don't have these carbonates that are underlying them. I just wanted to talk about it, and it's been talked about a lot already. This is basically, these are theoretical values of how many pounds of calcium carbonate per pound of nitrogen that are needed to neutralize the acidity. And these are based on some assumptions in terms of how those nitrogen fertilizers are actually used in terms of uptake by the crop itself and what happens to them in terms of transformations in the soil. But they're good to use just as rules of thumb. I often use, it takes, well, about 2 pounds of calcium carbonate to neutralize every pound of nitrogen that you're applying. And this is something that you could use not just to look at your past in terms of nitrogen applications, but if you're thinking about how much lime you're applying, you can kind of divide those tons by 2 in terms of how much nitrogen basically you're neutralizing in terms of the acidifying power of that nitrogen. You can see other forms. The sulfate here is contributing some to the acidification, as does the phosphate a little bit as well. What's not mentioned in this table is another process of acidification, and that's through leaching of the nitrate. So the nitrate itself is a negatively charged ion. It can move pretty readily. It's pretty mobile in the soil. It goes down into the subsoil. Well, we have a whole thing in science. It's called charge balance or conservation of charge. So every negative charge that's moving, it's got to be associated with a positive charge. So that's the charge balance. So where does that positive charge come from? It comes from the bases, often in the soil. So that's the calcium, the magnesium, the potassium, the sodium, also the hydrogen and some of the aluminum as well. But as that nitrate then leaves that zone of application, or where it was converted from ammonium to nitrate, whether that's at the surface or where you placed it from the standpoint of deep banding, as that nitrate moves down, it's taking with it bases, okay? And those end up where? They end up in the subsoil, or they can be exported and leached completely out of the profile as well. So that's another form of acidification. And in fact, for every pound of nitrogen as nitrate that leaches down, it takes about, theoretically, 3.57 pounds of calcium carbonate to neutralize that loss. So this is a real active form of acidification that can take place. And this is why we think that really narrow band of stratified acidification that we find develops so quickly. not just is it the ammonium converted to nitrate, which releases hydrogen, it's also the movement then of that nitrate down, because it's not all used right away, right? And we want it to move down, so that process also takes bases with it into the subsoil itself. We talked about all these acidification problems, and what's actually exciting is you can see from the group here that there's a lot of different people engaged. It's kind of a multidisciplinary kind of effort. pH really is a master variable. It impacts everything from the pathology to the weed science folks, to the agronomists, to the soil scientists, and to the breeders. So from that standpoint, it takes a collective effort. Everybody's interested in this because pH is so important from the standpoint of impacting so many things in our soil. So it's good to recognize that, but at the same time, it just also points to the magnitude of this issue of acidification. That's not going to go away. It's going to continue to be expressed, and more so over time. And many of you have seen these types of effects of acidity in terms of nutrients, and different nutrients have different kinds of reactions in terms of what happens to them under different kinds of pH conditions. I've just listed a few things that happen in terms of lowered microbial activity, phosphorus bound by iron and aluminum, losses of calcium, magnesium, potassium to leaching. That was just what I just described a little bit. The aluminum and magnesium become toxins as they are released into the soil solution. Molybdenum, which we just learned about yesterday, and which I think maybe would have been a factor in some of these pots over here. We learned yesterday, and you might remember, okay, what's the enzyme that's important in nitrogen fixation? Nitrogenase, right? It requires molybdenum as an essential nutrient. That molybdenum becomes less and less available as the pH goes down. And this is something that I've been applying. It's not really anything special, but it's resilience theory from the standpoint of soil health. Yesterday I talked about soil organic matter, obviously a key indicator of soil health. pH is also a really key indicator of soil health. But what we're interested in is what's healthy. What's the range of soil pH that's healthy? And it's not just in the topsoil, it's throughout the whole rooting depth that we should be talking about these kinds of things and talking about the conditions that that particular crop or plant is experiencing. So what is healthy? What value of that property, in this case pH, does it become unhealthy? And we're seeing, of course, that depends on what you're growing. Okay, different crops, different species have different sensitivities to this particular variable because of their sensitivities of what that pH is influencing, whether it's soil chemistry or other pathology kinds of issues. And where are we? What's the current state in relation to that threshold, that optimum? And how close are we to that? And then what's the rate of change? We'd like to know, okay, are we approaching some kind of threshold that we're concerned about in terms of pH? How fast are we going there? Can we slow down that rate of change or speed it up? Are we moving away from a threshold or towards it? And so these are kinds of questions that sometimes take longer term experiments in order to figure out, okay, and we've had a long-term experiment that's been ongoing. You saw Bob Mahler's, seminal research looking at soil pH over time, noting that in the 80s and then the 90s, what was going on with soil pH. And this is a long-term, basically, experiment showing that we've decreased about a half a unit every 10 years in general in terms of soil pH. So that's kind of the rate of change towards or away an optimum. It can also be thought of in terms of, okay, if I apply lime, how quickly does it respond? That's something that we were interested in. When does that level off? When does that kind of reverse if it does, if we don't continue with those applications? So that's kind of what we call the resistance in terms of how quickly things respond or don't respond. And then the management impacts. Okay, what are our options? And that comes back to what's our adaptive capacity. So we can see that if the pH goes on the Rockford area, they couldn't grow legumes after a while. That reduced their adaptive capacity, what kinds of options they have in the face of various kinds of, whether it's market uncertainties or other kinds of issues that impact, what your choices might be in terms of what you can grow. And so that type of, or it can be options in terms of whether we put this back into a CRP situation or apply lime or lime sources to it. So this is a little bit of a graph actually put together by Alex, who is right back here. Where are you? There you are. And this is using that type of theory to look at adaptive capacity. This is kind of defined as upper thresholds. Here's some lower thresholds, and those thresholds for legumes would be lower for wheat. Our breeding is actually changing some of that threshold stuff up. So, okay, so the tolerance stuff is actually one strategy then to change where that threshold is. We're lowering that threshold for wheat because that wheat is tolerant to aluminum in this case, or more tolerant to aluminum. And so we're changing it from the breeding technology standpoint. And this is that resistance. This is the rate of change that's taken place. This is 1940. We started off 7, a little bit below 7. The advent of a lot of work of a lot of application of monocle fertilizers. We've been going down steadily over time. And here we are, we're approaching, well, this is at 4.5, we're approaching system transformation. We'd be into blueberries or something else that actually was tolerant to really low pHs. I'm getting funny here in the afternoon, aren't I? A little bit, maybe, okay, not. But here's our adaptive capacity in terms of, okay, what can we do? We can keep looking at this decrease over time towards a more transformational kind of situation where we're going to have to really rethink if we don't do something. Here's the lime application. The resistance is really, it can be quite low in terms of things can change pretty quickly with a lime application compared to other things. Here's the CRP, that's the Conservation Reserve Program in terms of, okay, we could put it away for 10 years and see a slow increase in soil pH because we're not applying fertilizer and this type of thing, and the soils are rebounding a little bit. And then reduced nitrogen use is another one, okay? So if we don't apply as much nitrogen or are more efficient in terms of our application of nitrogen, we can also slow down this acidification process because that's a main driver. And you've seen this before. This comes back to those thresholds for different crops, right? Alfalfa tend to be pretty sensitive, and then going down through the various crops in terms of where those thresholds actually exist. And of course, we've been working down. We started off up here, right, in terms of, oh, here's pH against the bottom. That's 5.8, okay? So here we are way up here. We've been working on our way backwards over time, and that was that curve in terms of pH decline until we starting to hit these thresholds one after another in terms of impacts then on the crops that we're growing. So here's an example of just soil depth here. This is in centimeters, so this is, oh gosh, 5 centimeters. What is that again? That's like 2 inches. 2 inches, 4 inches, 6 inches, 8 inches. So here you can see the impacts then of where we actually deep band our fertilizer in these cases. So that's where the nitrogen is ending up. In our case, it looks like around 3 inches or so, give or take an inch. And you can see this definite stratification that tends to set up fairly quickly. Again, just a few years and we start to see this type of thing developing. And here on the other graph is just the aluminum. This is KCl, extractable aluminum. And this is nothing new. And Dr. Engel mentioned as we start to get below 5, we start to go up exponentially in terms of the amount of aluminum that we find with this particular test. And this is a threshold too in terms of, whoa, in terms of at what level of extractable aluminum do we start to consider things to be detrimental. And I think this is an area, I've heard all kinds of numbers, and I suspect that there's root systems that are impacted at lower levels of extractable KCl aluminum, but I think this is another area, and I've also heard 10. I've heard other things are in the literature in terms of amounts. Some of that comes back to the actual crops in terms of their tolerance to aluminum and other factors that are impacting this. But I suspect as we get above 2 to 3 parts per million of extractable aluminum, we're having some sort of negative impact. And you can see in terms of parts per million where that just goes up again very, very rapidly after we get below pH of 5. The other thing I want to point out is that much of Mahler's work in terms of developing those thresholds was based on a 0 to 30, a 1-foot sample, all right? So if we took a 1-foot sample of this, we'd find that we were up here someplace still. Here's the 1 foot. By the time we get to 30 centimeters down to the 1 foot, we're at 6. So we'd be mixing this all together, and that would be the sample we put in. Are we really capturing then the impacts of this stratification with that type of sampling? And what is the impact of this stratification where we have some locations that are way lower than we'd like to see, but then we have other places that are probably fine. And so does the crop itself able to navigate through this in terms of roots, et cetera? So this is still a question in my mind, and perhaps others, in terms of yes, we can see and measure this kind of thing that's going out, but how does this relate to those recommendations that Mahler was giving in terms of where those thresholds were, because that was a 0 to 30 centimeter sample, right, or 1 foot sample. So that doesn't translate directly into this type of phenomena. So if I say 5 here and it's stratified like this, I couldn't directly take that value and put it back on that graph in terms of seeing how much of a percent reduction in terms of the crops you would find. It wouldn't translate directly. So that's still an issue that I think we have in terms of trying to figure out where are we going to see responses to Lyme applications, is not knowing then, this again is this is all these data were based on 1 foot samples. But how does this stratification in turn then impact things? So that's still, I think, an area we need more work on. Another thing that people look at is not just the KCl extractable aluminum, but how much of the aluminum is on the exchange complex. So this is the cation exchange capacity of your soils. There's bases on those like calcium and magnesium, potassium. There's also, as pH acidifies, there's more hydrogen and aluminum that gets associated with that cation exchange capacity. These are the negative charges on the surfaces of clays and organic matter that hold bases that are relevant and interesting and important for nutrients. And aluminum can start to, as it becomes aluminum 3+, it's a 3+ charge, that can basically knock stuff off, bases off of that exchange complex, and be fixed quite tightly actually to the organic matter in particular. And so this then puts those bases into the soil solution, where in turn they can be susceptible to leaching losses, et cetera. And this is work out of South America. In Brazil, they have completely different soils there. Of course, it's a tropical type of environment, but their acidity is a real issue. And they've gone and basically lined the whole country that is associated with crop production, and done a tremendous job with that in terms of turning their soils around. But you could see, in this case, the aluminum saturation on the exchange complex, as that gets above, there's 25 right here, you can see root length negative impacts on root length as that aluminum saturation increases. And here's some of their work, again, with different tolerant wheat crops in terms of, again, the aluminum saturation. Anybody that reads Spanish, or maybe that's Portuguese, I'm not sure. And then here you have the yield of those wheat crops. And you can see as that saturation becomes above, here's 15 right here, so you definitely have an downward trend. So some of our highest levels right now that we have, and I showed you just a second ago, we're right around 16% or so. So the Cook Farm, we've been concerned about acidification, and we've gone forward with measurements with depth, and Tim was talking about some of that earlier. And I have a postdoc on that, Santosh now, who's contributed to this, that's actually gone through and made maps of a lot of this in terms of how pHs have changed over the course of time, from when we started this back in 1998, actually, and on through resampling in 2008, and then again in 2015. Tim already showed you this picture. This kind of shows that stratification. This is the 0 to 4 inch depth sample. We're definitely acidifying this piece of it in terms of the surface. And of course, with mixing of the soil itself through tillage, we tend to dilute out some of that acidification with other soil. So we use georeferenced sample locations. There's 369 points that we've followed through time. Not all these have been sampled to look at these analysis. About half of them. Every other point we've gone through and taken these profile samples that you can see here. This is a 5-foot sample. We go through and we divide it up by 10 centimeter increments down to 30 centimeters, and then by horizon after that, and all the way down to 5 feet. And you can see differences in light and dark, indicating differences in organic matter amounts, et cetera. Tremendous amount of variation over this 92-acre field that we can see just observationally from the standpoint of these soil cores. But it's these samples that we've then gone forward and looked at soil organic matter and also soil pH for looking at acidification kinds of issues. Here's some of the kinds of relationships you see in terms of pH. Again, here's the KCl extractable aluminum and going upwards as we get lower in terms of pH. Here's the base saturation. In other words, how much of that cation exchange capacity is filled up with our bases. Those are the good guys, right? The calcium and magnesium and potassium that are important for fertility, et cetera. And we're kind of working our way down. That base saturation tends to be very well correlated with soil pH. And here we're kind of we started way up here in many of our soils. This is at the topsoil, so they tend to be a little bit lower than subsoils, but we're around 80% or so. And then we're slowly getting below, and you really start to get concerned as you drop below 60% and getting into the 50s, et cetera, in terms of lower pHs and, again, the aluminum effects. And here's the aluminum saturation on that exchange complex getting upwards. Well, there's a high point up here that's 16. This is kind of getting up to and approaching those values that we found down in South America as well, where we're seeing responses. And then here's just the relationship between extractable aluminum and that aluminum saturation. Other minerals that are impacted, manganese also can become important from the standpoint of toxicity issues, and we haven't seen any of this as of late, but that's something that also starts to increase as the pH drops below 5. And phosphorus, this is one that I'm still kind of confused about, and maybe somebody can help me. Here we've got bicarb P and Bray P. These are fairly high levels in both cases, but in each case, as the pH is going down, those levels are going up. So our soil test phosphorus tends to be increasing as the pH is going down. What's going on there is a good question. In some cases, like the bicarb P, we're not supposed to be using that at pHs that are getting this low. But at the same time, we often think that phosphorus should be less available as the pH goes down and have more fixation by iron and aluminum compounds. And so this is kind of seems to be incongruity in terms of our soil testing and what happens as soil pH goes down. Look, this is an issue that I was pretty concerned about. This is a Thatuna. This is one type of soil that we have that's fairly common in the area. Thatuna series soils are very productive, highly productive soils. They tend to be in lower landscape positions. They tend to have high amounts of organic matter. There's a lot more water that's usually associated with these soils because of their positions in the landscape. And you can see that, first of all, and this is going down in the soil profile. So this is starting in those 0 to 10, 10 to 20, 20 to 30, and then down by horizon as we go this way. And you can see the range in pH here, generally lower here at the surface. But then you see some profiles like this one where we don't get much above 5.5 for the whole profile. What's going on there? So pH is remaining low throughout a whole 5-foot section of the profile. And so this, to me, was an immediate red flag. Okay, what's going on here in the same soil type? And here, again, same soil where we stay up above 7. Okay, so does this make any sense in terms of what's going on? And the only thing I could think about from this perspective was, okay, the hydrology of the field must be impacting something to do with the pHs that we're measuring in these particular situations. So that was kind of a hidden danger in terms of, well, how do we even address low pHs once they get beyond, our abilities to apply lime, et cetera, when it gets into the subsoil? Is that something that's going to be a real serious problem that we can't address if we have acidification that deep? So I'm going to walk you through a time series here with depth, going from 0 to 10 all the way down through to that subsoil to show the changes that have occurred in soil pH across this field. And again, this is all based on those georeferenced locations going from 98 to 2008 to 2015 in this case. And here, the red values always mean that it's pretty acid. In this case, those are about 4.5 to 4.5 to 4.9 pH is that lowest class in this case. These keys are all the same values from the standpoint of each layer, so you can kind of make comparisons right across here in terms of the colors. By the time we get into the yellow here, which tends to be the highest, we're about, it says 5.7 to 6.25. So we're up into what we would consider something that's livable. Here you can see quite a bit of variation, first of all, ranging from this 4.5 to about a little over 6 from the standpoint of changes. And you can see that when we started, and the past history before we started had been just a kind of a reduced till situation, right? So mixing basically of that topsoil, et cetera. And then in 98, we converted it, and our first crop harvested under no-till was in 99. So we've had continuous no-till ever since then, though we have changed up drills. So from that perspective, that's interesting to think about. So the drill we were using at first was a Great Plains drill. It's got a turboculture in front, low pressure fluid injection of fertilizer, and then followed by double disc and the same on 10-inch centers. And basically, you know, our capacity to penetrate the soil in our situation varied quite a bit. The fall, dry falls, trying to get fertilizer and seed in the ground was sometimes pretty challenging. So our deep banding wasn't very deep. And so a lot of fertilizer ended up pretty close to the surface. And on wetter springs, of course, we were able to penetrate much better with that particular drill and get fertilizer and seed placed a little bit more optimally. We switched over to the Horsch-Anderson drill, the Anderson opener, of course a Hoe-type opener, and much better in terms of our capacity, in our case, to get into the ground in dry falls and place fertilizer, et cetera. So we're actually able to place fertilizer more consistently at depth with the Horsch drill. And I think that kind of plays out a little bit in terms of even looking at these changes in pH. You can see things are getting redder to 2008. So from 98 to 2008, Great Plains, 2008 to 2015, Horsch-Anderson. And here I think a little bit of this effect we're seeing is due to our capacity to actually place fertilizer a little bit more better. But anyway, regardless, you can see that the uniformity of the pH is actually not so bad. So when we look at this stratification piece, it seems to be playing out across the whole field, regardless of what the background pH is across, you know, the field itself. And so, you know, it kind of lends itself to the idea, can we actually address just the stratified layer with a uniform application in order to correct that particular pH that's occurring seemingly everywhere in the field? So good question. So more things in terms of calcium. So here's soil pH again. As we're getting lower, the amount of calcium that's on the exchange complex is dropping down, indicating that we're losing bases out of the surface. Where are they going? Likely, at least in part, they're going down with the nitrate and going down into the subsoil itself, or moving away from the surface at any rate. And here's total bases, same story in terms of, again, on the exchange complex, total bases declining with soil pH. This is from topsoil samples. And then some of Carol's work for her master's degree program showing where we put down a sugar lime and fluid lime. And we were able, in this case, with about a ton of those materials to actually impact that surface over the course of less than a year. So here we actually were able to increase things from the control. And notice that these are what was that, about 2 inches at a time, I think our depth increments were. So we were trying to, sorry? 2 centimeters, sorry, 2 centimeters, so less than an inch actually. So we were working down because, you know, when you take a sample, say you've applied lime and then you come in and sample after a half a year or a year later to see and measure the impacts. Well, if you take a 6-inch sample and then mix it up, you just took all the lime that could have been at the surface and mixed it all together and say, oh, I had an effect to 6 inches, right? Well, no, you have to actually break it down in depth increments so that you don't have this contamination, basically, of lime to your samples that are below that. And so the way to do that, of course, is to take fine depth increments to actually see what was going on in terms of movement. And we know that lime doesn't move very quickly, right? And in fact, we've had other experiments with Tabitha Brown, et cetera, you know, with surface applied prills. in no-till situations under low disturbance drills. There's another factor, cross-lot drill, where even 5 years later we could not find stuff that had penetrated much more than about 3 inches or so, in terms of the impacts of that lime. So obviously submixing speeds that process in terms of getting the lime to locations that you need to have. We also, in this case, we're trying to use fine materials that we thought might be able to move more rapidly down into the soil. So the Moses Lake sugar lime in this case, as well as the fluid lime, tended to give us about the same results from the standpoint of its capacity to move down. And I thought that this wasn't bad, actually, in terms of addressing some of this near surface type of acidity under a no-till situation. So moving on down, this is the 10 to 20 centimeter picture next. And you can again see that gradually, and in this case, we're 4.5 to 5 is our red. Let's see, we are getting some green here. So that's getting into the 6 and 6.5. Okay, so we're slowly seeing, okay, there's some locations as we get deeper that are becoming less acid. Lots of variability here. It looks like the range is from about, well, in this case is about 4.5 and up to about 6 or so, or over 6 in terms of soil pH found in a field in the 10 to 20 centimeter depth increment. This is when we also started to think about different application methods to try to address that stratified pH. And instead of going through and just basically incorporating things, which is a pretty easy operation, and I'm not against it at all, particularly if it's shallow and it's periodic from the standpoint, okay, we need to get the lime down, let's go ahead and get this done this year. But this was a way to look at it from a more conservation perspective in terms of just looking at sweeps. Many of you are familiar with like a hay buster sweep, basically a 30-inch wide sweep. They come in, of course, different widths. We put, in this case, we went ahead and put a tank and a pump and then used just brake line to go through and have out the sweep every 3 inches. We had lime coming out the backside of this, and we could basically set this to travel about 3 to 4 inches deep. And we were thinking, okay, this is a bit easy way, maybe not so easy, but to go through the soil, not have the inversion tillage go on, kind of lift things up and not set too aggressively, but then still, and also target the application of a fluid lime source, which tends to be more expensive, but target it at where the pH issue actually was, and consequently use less fluid lime to address the problem. And we went through, we did this, and then we went through and after the application, we took this gridded form. This is a 1 foot by about a half a foot, maybe a little bit more. But you see all these little holes here. We took samples at each one of those. There's like, well, there's 36 times 2. There's actually 72 little sample locations here that are all mapped out. And we placed that against the side of a pit, and then we just took all the samples with a probe through these little holes here to measure pH. And we had a control, and then where we'd actually put this fluid lime down. And so what that looked like is this, and these scales are different here, but we started off 3.96 to a little over 5 in the control. And you can see that basically, and particularly in this one, you can see where we kind of wiped out these dark areas where it's more acid by using this type of a fertilizer or a fluid lime applicator. And so this could work in terms of addressing some of that issue and avoid some of the mixing that you may have with incorporation of a broadcast application. So moving down further, this is 20 to 30 centimeters, and you can see here, oh my gosh, lots of yellow. So that's the 5.5 to 6.5 pH. A little bit of green here and there, but not so much. But we've kind of gotten out of the zone then of where fertilizer is ending up in terms of application, and we're getting down into the subsoil where we're finding much higher pHs. But notice around the edge here that there tends to be some lower pHs. So this part of the field, if you know the field, this tends to be lower lying areas. The road runs right here. These are hilltops here. There's hilltops that range around here. There's a basin right here that drains then into here. And these are all the way around here. This portion of the field is all low-lying areas. So a very different hydrology occurring in those locations of the field, tend to remain wetter. Many of you are familiar with almost the subsurface irrigation that goes on during the course of the season, where those locations just kind of receive a lot of water that's infiltrated but hit layers in the soil that basically encourage the lateral movement of water and transport down the hill to these low-lying areas. And so you'll find that these areas are almost sub-irrigated from the standpoint of water. Also carries nitrogen and other kinds of things down there. So anything that's soluble kind of ends up down in these lower lying areas. So here we are in going down again. This is the next foot, 30 to 60 centimeters. And you can see, oh, interesting. In these low-lying areas, we're seeing low pHs. So I started thinking, well, what's that about? Good question. And then, so 98, 2008, and then here in 2015, we don't see them anymore, or at least not so much. So what's that about? So you can think about that. Anybody have suggestions? Okay. How we're actually ameliorating some of this pH issue over time, seemingly at deeper depths. Steve? Oh, yeah. Okay, so we're removing bases, right? So are we actually addressing the pH issues of the subsoil through leaching of nitrates down, but we're not leaching out of the whole profile, right? So we're still kind of using that nitrogen in the rooting zone itself. Some of them are going beyond that, the rooting zone, and leaching out, because we capture water that comes out of a tile line here, and we could actually measure, oh, we're losing bases out of these tile lines, as well as nitrate and other soluble kinds of ingredients. And that is another process. So these systems are still leaky, right? They're annual cropping. We don't use all the water that we could. And the water that escapes us, it's about 30% or so tends to leave the field. And with it it's carrying these bases and other things away. And actually, interesting enough, we made back of the envelope calculations that at the rate of the bases leaving the field right now, in another 100 to 200 years, we'll have taken, and looking at weathering rates, et cetera, of our minerals, will basically have stripped all the bases out at the rate we're going now, which is kind of interesting to think about from a longer term sustainability. But it also points to the fact that we're going to have to supply bases like lime back into these systems. So moving along here, and again, here we're down to, so this is the third foot. You can see more of this acidity showing up. This is kind of the headwaters of this basin that's right here. So again, a low-lying portion of the field, another low-lying portion. All these are low-lying portions where we're having pHs to begin with under our conventional history of 5.5 to 6. So our conventional history, remember, we had a lot of water that ran off the field. So we're not getting the infiltration. We're not probably moving as much of the bases down or the nitrates for that matter, down into the subsoil. So we've just significantly impacted the hydrology of this whole field by changing our tillage regime. So lots of runoff. In fact, if you look at the hydrology of these fields, you'll find that interestingly enough, the amount of water we lose through tile drains, which is around 30% of the precip, in our conventional system, we lose about that same amount, but it's through overland flow, surface runoff, and on into the ditch. So it tells you one thing, well, we're not using that water that we've infiltrated enough. We probably should be using more, putting it through transpiration, right, rather than losing it. But at the same time, it's saying that really significantly impacts and makes you think very differently about what water is doing to your soil from the standpoint of anything that's soluble, and you're increasing infiltration, et cetera. If it's going to be susceptible then to movement by that water to wherever that water ends up. And our water tends to redistribute over these fields, right? Hitting those argillic layers, clay layers, et cetera, that prevent the movement, vertical movement of that water down, hits those restrictive layers, and then moves laterally down the hills themselves, carrying with it whatever. And so I think that's what we're seeing a little bit of here, is movement of those bases down into the subsoil that are actually kind of correcting some of this acidification that some of our conventional till legacy is up here. So here again, here we're going to the 4th foot, and even more acidification in these areas in 98. And you can see that slowly over time, we're alleviating this particular situation with our direct seed system. So I guess that's the good news part of it. Over time, we're going to run out of bases, of course, right? So it's not something that's going to last forever. But if you just look at those pH changes over time, and this is just summarizing and averaging from 99 to 2000, we're acidifying basically. You can see the trends here, acidifying at the surface. And then if you look down here, you can see, oh, things are going up in the subsoil. And that's basically what those maps just showed us. And to take a look at the bases, this is from a subsample of those, and so it's not showing as much as I'd like to see in terms of just differences in base, but also gives you an idea of what those bases look like with depth, again, through the soil profile. And magnesium and calcium. And then you can see what the different one here is the potassium, which tends to cycle right taken up and then cycle in the above ground biomass. Not so much exported in the crop, and then it's ionic in the plant, so it tends to return to the surface here. So a different profile in terms of what that looks like with depth. Not surprised actually at how much sodium there was in our soil in some locations. There's actually more sodium than you might think. Some of Carol's work, and this is basically the soil test method to determine how much lime is required to raise the pH from an initial value up to some target value. We've often used, and the rest of the world pretty much uses buffered tests. These are rapid tests that are used in the lab in order to determine what the lime requirement is. And so, unfortunately, many of the tests that we have now regionally weren't really developed for our soil types. They're borrowed from other locations around the US and elsewhere. So that's the SMP is a common one, and the Adams and Evans are two common buffer tests that are used to determine what the lime requirement is. Carol did a fantastic job in terms of her master's to actually evaluate different buffer tests to see how accurate they were in terms of providing really good information in terms of what the lime requirement is. So this basically, what occurs is you have an incubation study where you take major soils from around the Palouse region that are acidified, you bring them into the laboratory, you incubate them over the course of how long was it, 3 months, 90 days? And with different levels of lime, okay, so calcium carbonate. So you can imagine all these little jars filled with different levels of calcium carbonate that are incubated in the lab over time, and then we measure the pH differences that occur then for that, and then we see how the buffer tests relate to that change in pH. So the buffer test then it doesn't take 3 months, right? That's a little bit too long to figure out what's going on, right? So these buffer tests then take a very short period of time and kind of allow you then to make a very rapid determination of what the lime requirement is. And so we tested out 7 different buffer tests, give or take. Thanks, Carol. And but some of the ones that really worked out well are this modified Malick buffer pH test tended to work out really well for us, as well as this Woodruff buffer pH test. This one needed to go forward. There's a correlation and then a calibration process that has to go on with this. But anyway, we found some really good correlation, some calibration still needed to kind of bring it in line to what the incubation was telling us in terms of how much lime was required. But these are not the tests that are normally run in our labs right now. And so, and in fact, the SMP and the Adams and Evans tests both gave us poor results in terms of actually providing a quantitative assessment of how much lime was required in order to raise the pH from an initial value up to a target pH. Often we were shooting at a target pH of 6. And then finally, I'm just, constantly, wondering about different things, transformations that are happening in our soil at the Cook Farm on conversion of no-till. That lack of disturbance leaves a lot of food for earthworms, those residues that normally wouldn't be able to have food. So the earthworm population has been going crazy out there. but some parts more than others. Okay, so here's a cross section of a 10-inch core at 5 feet. Okay, so they're going way past 5 feet. You know, you look into the literature on earthworms and say, well, you don't find earthworms below 6 feet. No, we've been out to John Ashland's. We've seen earthworm channels that are, 10 feet and more. If you've got soil down there, it seems like they just keep going down. And they influence all kinds of things. So I counted the number just from this cross section. There's 42 different earthworm channels going down. That's on average about 700 earthworms per meter squared. Oh my gosh. And you can see each one of these holes is coated with organic material. Also, it's a more favorable environment in terms of pH and nutrients. So here we have all kinds of variability in the soil that my Giddings probe, when I put a probe down, I hit or miss that type of thing. So I don't even know anymore if when I take a Giddings probe down, if we're actually capturing something that's representative that the plant actually sees. And the plants, you can see the roots that are going right through some of these channels down there. I'm sure they're taking advantage of all these nice earthworm channels and the favorable environments that are within them from a nutrient and water perspective, and who knows what else. And so this is something that I think is transformational that's occurring out there that I wish I had a better way of measuring it. I don't know how to even measure it. Sampling for earthworms tends to be fairly destructive. You actually have to dig the darn things up, and we wouldn't have any soil left out there. So from that perspective, I'm still looking for non-destructive ways to study earthworms. If anybody has any ideas about that, I'm all ears. There's ways to there's ways to put down different irritants, mustard gas to try to dry them up. There's ways to, when it's wet, to put in electric shocks in there, electricity basically to dry them out of the soil. All those tend to be somewhat time-consuming and issues in and of themselves in terms of studying them. But earthworms also, interestingly enough, have a calciferous gland in them. And this calciferous gland basically operates to take the carbon dioxide that is released during their respiration. So they respire. They're heterotrophs just like we are. So from that standpoint, they produce CO2. Well, CO2 is toxic in their bodies, and this calciferous gland takes calcium from the soil and combines with the carbon dioxide to create lime. Okay, so earthworms are actually a lime-producing agent out there, and they can be significant in terms of ameliorating some of our acidification issues. And we're increasing their population. So, I'm just wondering, okay, well, what impact are they having, and how can I study that? Because I don't really know. Thank you.